Good morning, everyone. So welcome to this very new world of remote conferences and virtual conferences. Normally, if we're all in the room, the people at the back would be closing the doors. The audience would have a quiet hush as they get ready. But we're just going to assume that's happening and everyone is joining remotely. So thank you all for joining us. I'm really looking forward to sharing some top secret cloud native security lessons with yourself. And the reason this is so important is because our systems are constantly under attack. Like every day, hackers and people, the mobility experts are looking for ways to break into our security systems for various different reasons. It could be to run Bitcoin mining, which is always a popular choice. It could be to just be disruptive and kind of take down your homepage and replace it with something else. Or it could be to start stealing secrets, start stealing customer data, which Troy Hunt knows all about with Have I Been Pwned, and or um, database credentials, user passwords, AWS secrets, everything else. And so it's our job as developers, as infrastructure experts to really manage that and really protect our systems. But the problem is there's so many different moving parts, there's so many different components now within our infrastructure that it can be really hard to chase all of these different exploits, all of these different features that get enabled, and then you need to tighten up and secure because it's not enabled by default. And so we're really fighting and really chasing. And this is what I want to start to demystify. I want to make sure that we understand the foundations, we understand what needs to be done at the foundation level, and the impact that will have if it's not done correctly. And we see case studies of this when it's not been done correctly all the time, with people like Tesla who accidentally left a Kubernetes dashboard open to the public, which got discovered, and then uh, hackers was able to run Bitcoin mining software or various different other cryptocurrency mining software on their infrastructure. They could steal AWS credentials, gain access to S3 buckets. It's pretty bad. And obviously the impact of that is people like me keep referring to it in a talk even 2 years later, which I'm sure all of our companies don't want us to continue to be doing. But as my title suggests, like, it's all about top secret. It's all about things that we are supposed to be sensitive and really being aware of. But actually, when it comes to security, top secret doesn't work. The whole point of this talk wouldn't work if we try and keep problems, try and keep security weaknesses to ourselves, because eventually they will be found, they will be discovered, and they will be misused in certain different ways. Now, to be announced does actually work. Like, we want to make sure that we are responsibly disclosing any security weaknesses, any vulnerabilities that we discover in a correct way, so that they can be patched, they can be fixed before the entire internet knows that they are that they exist. And we see lots of this in times where we have the rise of bug bounty programs, which are both popular for the likes of Facebook, Google, open source projects like Kubernetes, but every company should have an approach when it comes to a bug bounty about what happens if a security researcher does discover a open Kubernetes dashboard. Like, what happens? How can they responsibly disclose that to the organization so that it can be fixed, instead of them just tweeting about it, and then it turns into a panic and a stress while people firefight to get things fixed and get things closed. So the premise of this talk is what people should know when they're running Kubernetes fundamentally, but also just general cloud native systems, cloud native infrastructure, to make sure that things are secure and as locked down as possible as they could be. So to give you some background about myself, my name is Ben Hall. I'm the founder of Katacoda, which is an interactive learning platform for software developers. And we were recently acquired by O'Reilly Media. You'll know O'Reilly from doing the awesome books with animals on the front covers, conferences like Velocity and Strata, and many other various different activities in November of last year. And it's great to be part of this kind of larger organization now. For those who don't know what Katacoda is, it's an interactive learning platform for software developers. It's all free and available to everyone. And it teaches you primarily DevOps related topics. So how do you get started with Docker? How do you use Kubernetes? How do you make sure things are running securely? And various different security topics, cloud native related technologies, etc. And down the one side, you get step-by-step instructions, which show you how to solve particular problems and how to learn new skills, such as how do you launch a container. And then on the right-hand side, you have a live terminal session. This is a real live running system that's available to you directly in the browser without you having to download or install anything. And you can get started, you can explore, you can poke around, you can try and run various different things. And if it all goes horribly wrong and you break it, you hit refresh and you're given instantly a brand new environment so you can start all over again. And hence, as you can imagine, giving people an open terminal window where you don't need to log in, where you don't need to sign up, you don't need to enter any credit card details, has caused us some interesting security lessons. And that's kind of the context and the background about where I'm coming from in my talk today. So as a quick refresher about what we're going to be talking about, a lot of the lessons I'm taking are from the real world. It's things which we've seen in the wild. It's things that people have been exposed to, and things which you may be doing internally and not seeing the impact or not understanding what the side effects of that could be. We can then take a bit more of an academic researcher-based approach to the lessons. So looking at various different security audits that have been done on Kubernetes to see what people in the industry, security experts, are looking for, and to try and identify, can we predict that this could be a problem, or can we actually see problems which we have in our own systems which relate to other problems in Kubernetes and the wider industry, and generally interesting lessons learned about where security bugs actually come from in the first place. And then finally, we'll look at some recent disclosures from 0 days to see what the impact is looking like today. And then how can we make sure that we are secure? What can we do to prevent all of these things happening? And is things like Istio and service meshes and the future going to actually save us from all of that, or are we still in trouble? There's Q&A, so please do take advantage of this. Please do drop in messages as I'm going through everything, and then we'll get some time at the end, which I'll go through it. Otherwise, just drop me some tweets or drop me an email. I'm always happy to go into more details on this topic. So let's start from the foundations. From a security point of view, given Kubernetes, what is it that I actually need to be paying aware of? And what is it that I need to know from the foundations and from getting started? So the first thing to know is that Kubernetes is dramatically getting rapid adoption across the entire industry. It's not full adoption, it's not mainstream, but it's definitely on that trend towards it being there. All the cloud providers are now saying that this is the way forward, and this is the way that it should, that they're pushing that applications deployments should be around a container-based orchestration with the rise of things like Elastic Kubernetes Service, EKS, the Azure Kubernetes Service, GKE, Google's Kubernetes Service, etc. So everyone has these movements towards running Kubernetes as the starting point. Now, with this rise, it also brings more attention from a security and hackers point of view, because they're now seeing the popularity, they're now seeing more adoption of this platform. So it's now making for a much more interesting target in terms of finding a potential exploit and then being able to access people's systems. But on the flip side, if we add this nice little red chart, obviously, when it comes to Kubernetes, that's really popular. But when it comes to things like Kubernetes security, it's definitely not on the same trend and definitely not raising as much awareness. But even though it's a critical part of what we need to be paying attention to. So we just need to be starting to raise awareness that Kubernetes needs to be secured. We need to take that into consideration. And we need to make sure our systems have the right defaults in place. So just being aware that it is still a concern. Kubernetes is not a magic bullet which instantly makes your system secure, reliable, stable, scalable, and all of the other interesting buzzwords. If we look at the architecture of Kubernetes, there's a couple of main components which are interesting from a how does Kubernetes work, but also interesting from what a security researcher or an attacker may be looking at in order to find ways into your system. So in this case, we've got a master node. So this is running the Kubernetes control plane. And then we have two worker nodes, which is running the containers, which will be running your applications and all of your components. So the way we interact as developers with Kubernetes is via kubectl. This is a command line tool that you run locally. It's got your credentials. This is what you'll do, like kubectl apply from your local dev machine or like a Jenkins or a GitOps workflow in an automated way. But there'll be some interaction to the API server. And this API server is a gateway into Kubernetes. It's like, this is what we tell Kubernetes how to do something, how we gain information about what the current state is, and basically manipulate and update what the Kubernetes cluster is doing. Now, The API server is responsible for communicating with the XCD under the covers. XCD is the database which is maintaining all of the state of the Kubernetes cluster. And this is everything the Kubernetes configuration has been applied. So all of the pods which have been running and their configuration, any secrets and passwords which have been persisted, any security certificates that have been enabled and applied to the cluster configuration, and everything else. This is the heart of what Kubernetes infrastructure is. And so that makes it for a really interesting target from a security point of view, because if you get access to the XCD database, you have access to all of the information, all of the secrets, everything which you actually need. Now, obviously, the API is the third thing which people are interacting with. That's the front boundary of Kubernetes. So that's also an interesting target, because if we can start changing or manipulating or finding weaknesses within the API, then we can then use that to potentially get access to XCD. And then finally, the worker nodes themselves. Like these are the hosts running our workloads. And so if we can find access or find a way in to gaining access to one of those hosts, then that gives us access to potentially running additional things on that machine, finding additional logic or functionality, or finding a jump into other parts of the systems. And these are the types of things which people are looking for, and these are the types of things which we need to start defending against. Fundamentally, Kubernetes is just a big loop. So what's happening is when you're telling Kubernetes to do something like deploy a pod, that's going to the API server to change the state. And then internally to Kubernetes, there's lots of controllers and lots of things being observed. When our desired state, i.e. we should have this pod running, changes, then Kubernetes will step in or figure out what needs to be done in order to make that happen, and then issue those commands, change whatever needs to be done, and then it'll go back and round and looping. Now, this is interesting just because if we can jump in, or if we can observe into this loop, then we can see what the cluster is doing, and we can observe and we can interact and potentially manipulate the state of what Kubernetes thinks is happening, which is always interesting and something which we'll get onto later on in the more interesting aspects. But before we get into that, we need to start thinking about how do we apply security from like ground zero, like what is the fundamentals that we need to be applying, and what's the impact when we kind of go beyond, or we misconfigure, or we have something which wasn't quite as expected and open us up to problems. So the first thing that we constantly come across is people accidentally leaving their Kubernetes cluster open to the internet. So this is how Tesla got their impact, and how Tesla had Bitcoin or cryptocurrency mining happening on their infrastructure. And it was because they left it open to the public. And we can go to Shodan, which is a great tool. It's a search engine which will show you all of the IP addresses and the response codes, which when they send a HTTP request or HTTPS, what response code is coming back. And so from here, we can see that a lot of the response codes are coming from saying they are Kubernetes clusters. They're saying they're Kubernetes masters. And so we can also see that there's lots running in of AWS and Amazon, which is potentially running either COPS or the Google Elasticsearch, which wouldn't be open to the internet unless you've done something wrong. But this is now given us a hint into potentially vulnerable systems, because we now have an entry point to gain access to that API server, because that API server is being open potentially to the internet. And we can start drilling in more into these responses to see what's interesting and what's being actually reported back to us. So things like COPS will report DNS entries as part of the certificate that's created. So we now have an insight into the default configuration that would have been applied, or the types of infrastructure that was used to be set up. So if we know that COPS has a particular default, which is vulnerable, or some practices which may not be as secure as it should be, then we can start using and looking at and poking in that way to see if we can find an interesting attack vector. Others are showing that they're an internal staging or an internal testing system, which is interesting because if it's internal, it may have had people learning, people experimenting on that. And so it may have had some security weaknesses changed or security settings changed, which is introduced as vulnerability because it's only meant for internal usage. But if we can get into an internal system, then maybe we can find some internal kind of certificates or more information, which is useful for people to then get into production or find more about the production infrastructure because it's not had a proper boundary set in place. And others will just quietly say that they're a huge private equity company with lots of assets attached to their platform. And so they're telling you that they're an interesting target and that their Kubernetes cluster is a test cluster, so it potentially isn't as secure as what their production system would be. These are great information that you just get for free by typing it into Shodan and seeing what comes back. So making sure that we're not exposing this to the public is always a good starting point. But let's say we do, what's the worst that could happen? Like, isn't it secure by default? Well, it is until you start tweaking the configuration of what Kubernetes allows you to do. So that by default, Kubernetes is secure if, in terms of anonymous requests, that's disabled and you have to have a security token. But if you're trying to bypass or trying to get something working, you may accidentally or intentionally turn it off with the intention of turning it back on later and then forget. So things like allowing anonymous authentication, because there's a dev server and we don't want to deal with authentication, we just want to get it working quickly and it's never going to last long. We may just enable that by mistake, not realizing that the entire then API server will just accept anything. And if we accept any API calls, then anyone can start any pod or any deployment on our system without any limitations, without needing to be authenticated. And so these systems are allowed and they are enabled by if we needed them to, which is dangerous within a dev situation. We can also just run it accidentally by setting a command from kubectl. We can tell Kubernetes to create a new cluster role binding, which is the authentication approach in Kubernetes. We can give it a nice name like cluster system admin or anonymous. It can have the role of cluster admin. And then for any user who's reporting themselves as anonymous, we just say, sure, if you're an anonymous user, you can now be cluster admin, which is pretty dangerous. And you think like no one would ever run that. That seems like people would see the impact. But that is until you see the responses to Stack Overflow questions and other things online, where people are hit with very confusing, very complex issues within Kubernetes, such as why don't I have permission to do this? And they're just trying to get out of that problem. They're just trying to unblock themselves just so that they can learn how it works or just how they can get to the next stage. And so they will go, cool, if you want to remove that error, run this command to make anonymous access ever be automatically cluster admin. As a side effect, now any API calls instantly becomes cluster admin. Anyone can do anything to your cluster, and suddenly you have got no security protections within your system, which obviously is a huge impact. So this was the case in the very early systems of Kubernetes up until 1.16, and then 1.6 introduced RBAC. Now, at the time in 1.6, a couple of years ago, this broke everything, but it was important to introduce this so that we have role-based access control. We can start to define what a user can do and what impact they can have in a system. And so instead of everyone being cluster admin and every application being cluster admin, we can start breaking it down into, well, this application or this user can only read the pods or only read the deployments for everything within namespace A or namespace B, which is related to their project. And so we can now start taking a huge Kubernetes cluster and slicing it into very discrete kind of access controls based on what that user needs, and start taking a least privileged based approach to our configuration. And so if we look at what the cluster admin, which is not the ideal security mechanism in place, we can see that we have the role, and by default, it has access to everything. Star meaning that every single API, every single resource like pods or secrets or deployments, and every single verb. So they can list, they can get, they can delete, they can read, they can create and update. So cluster admin has access to everything. Where by using RBAC and creating a much more defined role for our applications or for our users, we can start to break that down. We can say that actually this pod reader only can list all of the pods running, and they can only do read-only changes. They can only list everything, and they can get the details of what that pod configuration is. So now if we know that a user doesn't need complete access, we can create this role which gives them a lot more fine-grained permissions. And if this credential then gets leaked or accidentally gets applied somewhere, it's not going to have a huge impact as it would if we gave everyone cluster access. And we need to be somewhat careful about how much information and some of the APIs. Like if you list a secret, it gives you access to be able to get the base 64 approach. And it's fundamentally, I think it's important to remember that the secrets inside of Kubernetes aren't secret. They're just base 64 encoded strings. If we want to make sure that our credentials are truly secret, we need to use something like a secrets manager within Google Cloud or HashiCorp Vault, which will encrypt and make sure our secrets are actually secret, not just base 64 encoded, and not just accessible via an API call when you list out all of the secret information. Likewise, when we create a pod, like a pod you would think would be fairly harmless, but in reality, a pod can have lots of different configuration settings applied to it. So in this case, we've got the auto mount of a security token, and we're saying we want to get a service account from within Kubernetes. And as such, if we map those in, they can then get the token for that service account user, and then we could potentially use that in other ways. In this case, we're launching a reverse shell. We're also saying that we can expose the host network, so we get access to the host machine and more information from within our pod definition. So when we're thinking about our role definitions and thinking about how we start breaking it up, we need to remember that just because it can create a pod, that impact of creating a pod can lead to additional settings being applied, which have a greater impact. And we have some slides later, which will show you how you can also ensure that even if someone tries to apply this config, it gets rejected because it's not allowed to access the host, for example. Kubernetes has privileged escalation built in. So if you have someone have got a role, then they can't elevate themselves even if they have the ability to do it because this is applied. So Kubernetes has taken lots of considerations in. When it comes to accessing Kubernetes, we've got this role. When we start the pod, we can give it the service account name, i.e. the role of the user who's been assigned that pod. So now our application running inside of a pod can access our API, can do the things it needs, but it doesn't have complete permissions. And that's only if you need to access the Kubernetes API. If you don't need to access the Kubernetes API, you don't need a service account. You don't need a token being injected in. So you should automatically make it disabled by default, so that actually there's no token being injected in, so there's no concerns about that application being exploited and then using that token to attack the Kubernetes API and find potential privilege escalations within our system. And so this is the default now in the latest version of Kubernetes. If you're running a previous version of Kubernetes, then you need to make sure that you're actually applying it if you don't need to access the Kubernetes API. So that's kind of an insight into RBAC, and like making sure that we have the right RBAC configuration settings in place, and we're taking that into consideration when we're deploying our application and when we have people managing our cluster. But what other defaults do we have which are both good and bad? And particularly good and bad from the Docker's point of view, because Kubernetes is fundamentally just using Docker under the covers. So we need to be aware of what Docker can offer us and the impact and the benefits that brings to the situation. So the first thing which I always love about Docker is the ability to run a privileged container. A privileged container is a container which has got 0 security permissions applied to it. And so in this case, I'm in an Ubuntu bash prompt. I can see that there's a disk called VDA1. I can mount that disk into a temp directory, and that VDA1 is the host, the disk running on the host itself. Because I'm in a privileged container without any permissions, I have mount access and I can mount any drive I want. So now I have access to the host disk without any security sandboxing or security limitations. And if I have access to the host disk, I can do things like manipulate SSH keys. I can add in my own SSH key into the authorized keys file. I can then, if it's access to the internet or has access to the internet, I can then SSH in from the outside world and gain access to the host, all within 3 or 4 commands. Now, this is a kind of a huge problem if you are running privileged containers without needing to, because if your application gets exploited somehow through a bad API or some vulnerability in a component that you're using and it's in a privileged container, people can then run commands and be able to manipulate the host and potentially gain further access than what you would expect them to be able to do. So privileged flags should be called insecure. It shouldn't be used unless you know the implications and you know the impact, and you have other security mechanisms in place to protect against it. But for 99, maybe even 99.9% of situations, it shouldn't never be applied. But it can be set through the Kubernetes API, so it's important to know why we shouldn't do that. The other is things like if people get access to a pod, even though it's running in a pod and it's not in a privileged container, so it has the default sandboxed capabilities applied, they can still start causing disruption to every other pod running on that Kubernetes node. So this is a great command. It's a bash command that you can type in. I wouldn't recommend that you do it on your local machine, because what it's doing is it's defining a bash function called colon. The body of that function is calling a function called colon, which pipes the output to a function called colon, and then releases control, which is the ampersand. And then once that function's been defined, call the function called colon. Now you can see this happening on a host because your system load will go to 4,000. You'll have 7,000, 10,000, 20,000 processes instantly being started because we have this fork bomb type mentality of everything calling itself multiple times. And then your system will just run out of resources and everything will grind to a halt. So all of the pods will crash and you'll have to do a hard reboot on that host because there's no resources left to be able to log in and do it via SSH or other mechanisms. It needs a hard reboot. So we need to make sure that that is being protected against. So so Docker's had this for a very long time. The ability to set a PIDs limit, so how many processes a container can be running. And this has been recently introduced into Kubernetes at 1.14 and beyond. So you can set when you start your kubelet, the kubelet being the process which is managing a Kubernetes worker node. When you start that configuration, you can set a max limit for all of the pods on that host. And so you can set this to something reasonable, like 1,000 or 2,000 processes per pod, because it's very unlikely that anyone would be running more than that in an average system. And what it means is by having this sensible default limit applied, if someone does manage to break in, if someone does manage to exploit the application and they try to just be disruptive, they're going to hit this PIDs limit and they can only run 2,000 processes and not take down every single pod on that machine. Other things to do is like we've seen privileged and we've seen the impact that can have if you run privileges. And so we don't want to be doing that. But what you can also do is remove additional capabilities from our defaults. So when you start a Docker container, it has certain Linux capabilities attached to it. For example, netraw. The netraw capability is a grouping of permissions which tell Linux how certain things need to, in order for certain things to work, it needs to have this capability, which is a grouping of permissions. So in this case, netraw is the ability to open raw network sockets, for example, pinging other machines or other hosts. So most normal running applications doesn't need to create a raw socket. They don't need to create a raw outbound connection because they're just normal everyday web applications. And so we should remove that capability by default so that if an attacker does get in, they can't create raw sockets to an outbound host or to other parts of our network very easily because they just don't have that capability in place. And there's lots of various other Linux capabilities that we can remove to ensure that the pod running has the most reduced service area possible. So we removed all of the potential functionality that just isn't required in a default configuration setting. And then we only apply the 1 or 2 capabilities that's required in order to make sure our application is functioning correctly. And we can go even further on that with sepcomp. So Linux capabilities are the ability to have a grouping of a particular functionality, like opening network sockets, changing the system host name, changing the time, adding users, mounting file permission, file systems, etc. Seccomp is the level below that. This is like what system calls can our pod be making, or which system calls should be blocked from our pod. And so you can imagine this would be things like, can it change the file to mod file permissions? Like, can we make a file from not being from being read-only to being write access or executable by changing the Linux permissions? And so by default, a lot of these are blocked by default, but these can be changed, and we can lock it down even further if you want a really secure, really locked down, tightened up system. On the flip side, we need to make sure that if we've applied a profile, we're not opening it up to everyone and not allowing everything, because then accidentally we've removed all of the capabilities and all of the blocking for potentially malicious system calls, such as mounting a file system or installing a Linux kernel module. The example I have on the slide is that the default action for my profile is to allow everything. This, by default, will not have any security permissions in place, and is so a pretty bad default if that was to be applied to my cluster, because someone will be able to exploit it and run things which they shouldn't do. Unfortunately, Docker's got a great whitelist by default, but if we're changing those in which we're configuring it, we need to be aware of the impact. But we can make sure that there's a limitation into how much people can apply. So there's a flag called allow privilege escalation. And for me, I always set this by default. This flag ensures that if you set the user to run as a low privileged user, such as someone without permissions, which we should all be doing, such as user 1000, they can't then do certain things to make themselves to become a root user, which is full access to everything. And so by blocking this blocks certain system calls or additional system calls that Linux have in place, and make sure that the user will always stay as the low privilege user that we've defined in our security context, and they can't accidentally become root through an exploit or through a kernel hack or through some misconfiguration. The same applies if we're running in Windows. We don't want Windows users to be running as root in exactly the same way that we don't want Linux users to be running as root, because as soon as you have root, you have access to install additional packages, additional configuration. And so in Windows, we have this concept of container user. This is going to be more important as people start moving traditional workloads from VMs into Kubernetes. With the rise of Kubernetes support for Windows, we're going to see this more and more frequently. And so the same applies. The considerations we're taking into account for Linux need to be applied the same for Windows. And so this case, we're saying it's running as a low privilege container user, and so additional things can't be installed or settings can't be changed. So these are some of the fundamental defaults that aren't applied by default, or some of the considerations that we should be applying which aren't applied by default within Kubernetes. So making sure our users aren't running as root, making sure we have sensible PID limits, making sure that we turn off tokens if we don't need them, and various other things. But what's happening below, like we're all building on top of Kubernetes, we're all running it. What's happening under the covers, which we may not be aware of? And so the CNCF, who's the governing body behind Kubernetes, has done audit reports on Kubernetes. It's gone out and it's hired external third parties who have looked at Kubernetes and have done a proper security research on those. And the white papers and all of the information is available within GitHub if you want to go read it. Read more about what security impacts there are, what the threat model looks like, i.e. where are the vulnerable parts within the Kubernetes system, which is the thing I was mentioning at the beginning, but it goes much deeper than that one slide, and basically gives you much more exposure to what Kubernetes is doing under the covers. And so it found there's different things within that security report, which kind of advises you on the best practices to be taken. So for example, that example I showed you at the beginning where you can enable anonymous requests, like we should be making sure that we don't have anonymous authentication enabled. And that is a configuration setting that we should probably turn off and completely lock down so that everyone has to have a security token, not just that they don't have any permissions or they don't have any access control, but they should just not be able to make any API calls in the first place. So at the moment, by default, that's true, but we can go in and we can change the configuration so that we can completely remove system anonymous. And so if someone had accidentally ran that command I showed you at the beginning, it wouldn't have had any effect because that system anonymous user would no longer exist. The second security report which got applied goes even deeper. This goes into more of a code review at a systems level. And so this has got also some really interesting approaches and some interesting kind of attack vectors, which I hadn't considered to be potentially a problem. So for example, being able to cause an out-of-memory error because you have an API which returns a very large YAML definition, which is invalid. And so the trends being we all used to do curl to a bash prompt to install something. We're now doing kubectl apply of a file from a remote system. If that remote system got taken over or got a malicious actor kind of taking advantage of it and replacing what that YAML definition would be to being something very large, then that would potentially cause an out-of-memory exception for the Kubernetes cluster because they could just send down a very large YAML definition, which I thought was like quite interesting and a fun approach. But there's more kind of severity and more kind of interesting approaches which you're thinking about depending on your security approach and definition depends on how much of an impact it has. But things like if you are running on a multi-tenanted system where you're using namespaces within Kubernetes to sandbox and isolate different components or different users or different tenants within your cluster, based on how DNS works, the core DNS which is used within Kubernetes doesn't have a concept of namespaces. So because that doesn't have a concept of namespaces, that will report information being reported back to it across multiple namespaces. So then you can find other information about what's happening on that cluster above and beyond where your current pod is running. So in this case, we're asking and doing a DNS lookup on the default service, DNS entry, and then that's returning things like there's a WordPress instance running. And if we can then find a way in, we know that WordPress is available here, then we could load in an additional exploit, for example. And so we need to be aware that the certain security permissions at the top, like namespaces, don't always necessarily filter down to other components that Kubernetes is building upon. And then we see other things like other security permissions that get applied, which we may be utilizing without understanding the security impact that they're having. So things like host paths. So the ability that we can bypass various different volume restrictions that we may have thought were in place because of the host path configuration that's been applied. Now, I think this has been fixed by default, but it's these kind of lessons that we need to be taken into account and kind of considering and seeing what impact they would have on our system and the functionality which we're using in Kubernetes so that we can make our own adjustments or our own tweaks to configuration based on our own situations. So there's lots of interesting conversations. If you're interested in learning more, it's all on GitHub. All of the issues discovered are GitHub issues from the security findings. So you can go here and that will tell you some more information. What you'll also see is after this report was announced, all of the cloud providers did various different updates and security announcements, which is one of the benefits of having running on top of a cloud provider is that they'll be updating and making sure that anything which gets discovered will be rolled out to your cluster appropriately. So while that is vulnerabilities within, or this report disclosed or discovered vulnerabilities within Kubernetes itself, other aspects also were highlighted. So things like the fact that HTTP2 had a denial of service attack vulnerability, and so because it was building on HTTP2, it had the impact of having that effect within a Kubernetes cluster too. And so it's not just what we are building on layers, and Kubernetes is building on layers too. And so it's all filters down. And so from a security research point of view of like, if we're responsible for the security, we need to be aware of all of these various different moving parts, or being aware that these security vulnerabilities may happen in something which we, in a place where we didn't necessarily expect it to happen. So we need to make sure our cluster is as secure as possible. And these are various different examples which I'll leave in. The slides will be on Twitter afterwards if you want to drill in some more information afterwards. But we have all of this information. We have potential misconfigurations. We have potential Docker misconfigurations happening. We have potential vulnerabilities in the real world through security researchers which are being discovered. What impact is this going to have for us as people running on top of Kubernetes? So the first is that we can actually see like people misusing Kubernetes in interesting security ways if they gain access to a cluster. So the first one, which I really like, is the ability to run daemon sets as an exploit. So a daemon set is the ability to run a pod on every single host or every single node within our Kubernetes cluster. And so this is great for things like monitoring purposes, or if you run Prometheus or Datadog or New Relic, you can run that as a daemon set and ensure that every single node automatically has Datadog agent or the New Relic agent automatically running on top of it. But this can be misused, shall I say, if an attacker gets access to the Kubernetes cluster. So if we get access to the Docker host, we can run a reverse shell, which is the command at the top. So this is from Rory, who's a security researcher, which is doing some great work. He's running his Metasploit version, and he's saying it would create a reverse connection to this IP address on this port. And this same kind of impact and the same command can be run as a daemon set definition, which is what we're seeing below. We're also hooking it in to, we're being able to run that because we're mounting in the Docker socket, which is what we're seeing with this volume mounts and the volumes at the bottom. So the daemon set is going to be run on every single node within our cluster. It's going to mount in on every single node the Docker socket into our container. And then when that container starts, it's going to create our reverse shell. So now if we get access to an API or to the API to be able to run a daemon set, maybe through the misconfiguration I mentioned, then we now instantly have access to a reverse shell running across our entire cluster and access to all of the nodes running, which gives us kind of unrestricted access to everything. So this is always fun implications. There's others that we could hook into the how Kubernetes works to start finding more information and start capturing information as it's being deployed and as it's being changed. So this is from a great talk, which I mentioned at the end, called on Advanced Persistent Threats in Kubernetes, which was delivered by Ian at the RSA conference. And this is all about using validating webhooks as an attack exploit. So as I said at the beginning, Kubernetes is just one big event loop. It's one big controller, and it's looping around and deciding like, should anything happen? Should I deploy a new pod? Should I deploy a new secret? Does anything need to be changed? And it's constantly checking. Now, there's various different hooks that you can do in order to hook into that to see whether certain permissions should be applied or whether certain things can be deployed. Like, we want to make sure that we're not deploying untrusted containers or containers which have security weaknesses. And to do that, you can have this validate mission webhook. But this can also be manipulated. So if you deploy a webhook or this admission controller, you get hooked into all of the events happening within Kubernetes. So for example, a new secret being created. Kubernetes will helpfully go to this validating webhook or validating controller and say, is this secret allowed? The controller, being slightly malicious, goes, sure, of course this secret's allowed. And it will always say yes. It will also push that secret to an external service. That external service now has our secrets, and Kubernetes has validated everything and deployed it as normal without having a hook in place. And so it's this ability to interact with the API, the ability to deploy additional components, can lead to weaknesses that go undiscovered or potentially look harmless from a security, from a administration point of view, but potentially doing things interested under the covers. One way which we can defend against things like this is by using network policies, which are a default feature within Kubernetes, and they can start restricting what pods can talk to each other within our system, or what namespaces or components can talk to each other within our cluster. What it can also do, if we combine this with things like a service mesh, like Istio or Linkerd, we can block all of the egress traffic, so all of the outbound traffic from our cluster. And so what we can do is we can block that, and we can make sure that it can only talk to our internal systems. And so if something does manage to break in, or someone does manage to inject their own component into our pipeline and get it deployed into production, the egress gateway from Istio or Linkerd will actually be blocking that outbound connection to making sure that they can't open a reverse shell, or they can't push secrets to an external service, and making sure that if the worst things happens, there's still an extra boundary that they're going to have to jump through in order to make sure that that's in place. And for me, there's very limited reasons why we should allow egress. Like if we're going through a proper CI/CD process and everything gets built, everything should be, there shouldn't need to be any updates. There shouldn't be any packages being installed. There shouldn't be any new components being deployed onto it, because that should all happen at build time. So the ability that we can do an apt-get update in a running pod is a security weakness. If we do need to talk to an external API, like maybe a Google Cloud API or something else, we can just whitelist them. We can say, yes, you're allowed to talk to these 1 or 2 external APIs, but everything else is restricted, to try and be secure by default as possible. But there's lots of moving parts, there's lots to understand, and there's this tower of components that we're building on, which we all need to make sure is secure. So how is that actually feasibly possible when you're running and trying to do 1,000 other things at the same time? So the first thing to do is make sure your team is well educated, obviously. Tools like Katacoda you can follow for free. You can play around with these settings within the sandbox environment within your browser. You can see the impact, you can see the security risks, and you never have to run them locally and accidentally make that mistake while you're learning and experimenting with Kubernetes, because it provides you with that safe sandbox. There's also various tools that you can run against your cluster to make sure that misconfigurations haven't been applied or haven't happened. So kubebench from Aqua Security is a great tool. It runs as a daemon set, and it will give you a report about every configuration that's been applied across all of the nodes within your cluster, and it will tell you whether you've got security implications as a result of misconfigurations being set, or defaults not being, or security settings not being applied correctly. So it'll give you a nice report from a command prompt. It's also got a great PDF and report, which will go into details about what those settings mean and the impact of having them set either false or to true, or in a misconfigured way. And so you can now use that to analyze what changes you need to be made, or if any security problems have accidentally been introduced. We can also do this at an application level as things are being deployed onto our system. So KubeSec is done by a security consultancy here in London called Control Plane. And what it would do is it uses that validating controller that I mentioned, which can do interesting things and potentially push secrets to external services, but it uses it in the correct way of what it's meant to do. So for example, if your YAML definition has a security setting which it shouldn't have, or if it's missing a configuration, it will actually perform a check on that YAML definition to see, does it apply to your corporate policy or the rules that have been defined by your infrastructure team, to make sure that you're not accidentally running something in an untrusted, insecure way. So for example, a pod which is trying to access the host, or a pod which is running as root. You can enforce that at the cluster level to ensure that those potential vulnerabilities never impact production and never make its way to the system, which has another layer of defense that an attacker would have to work around and get around. This is also applied via a pod security policy. And again, this defines what pods are allowed what configurations are allowed to be utilized by a pod and which ones aren't. So for example, for this security policy, we're saying that you're never allowed to use privileged containers for the reasons I talked about earlier. You're never allowed to use host maps or various different types of volumes. You can't use the host network or gain access to the PIDs. It must always be running as a non-root user, etc. And so again, you can start enforcing this at the cluster level to help with that education about what's expected from people deploying applications onto your cluster. And a new thing which is coming is an open policy agent, which is taking that the pod security I mentioned here and creating more advanced controls and more advanced capabilities, being able to talk to external systems or other APIs to see what is and isn't allowed. This is part of the CNCF. So if this is something which you're thinking about within your organization about how do we protect against this and ensure that our systems are always secure, deploying secure components, this is a great tooling to start considering. And then you can write these rules which say things like, you should only ever be deploying a container from our internal Docker registry. For example, these two running on AWS. Everything else which tries to be deployed, which isn't from our registry, gets rejected instantly. So a really great way to ensure policies and ensure that you're always running securely. So what are some recent vulnerabilities? Like what should we be slightly concerned about? So this isn't a 0-day, but it was released towards the end of the last year. This was a way to bypass AppArmor by just copying over some files into a container image in the right locations. So AppArmor is a Docker feature or like a Linux feature which Docker uses to restrict how much access it can do. So things like blocking write access to certain components, blocking the ability to mount certain files, etc., and provides an extra level of security vulnerabilities. If you can remove that capabilities that Docker have in place and override the default policy that is blocking everything, you can gain access to the host. And so if you gain access, you can do things like mount the file system, you can change system configurations, inject kernel module hooks, rootkits, etc. And so this, like the ability that you could do this at a container level, if you manage to run that container on a host, you gain access to the entire host. And this is why when cloud services are trying to let people run containers on their system, they're always doing it inside of a VM or a hypervisor technology such as Firecracker. And that's why AWS has built Firecracker, because containers cannot be trusted. And that's why you should always make sure that you're building the container and not just taking it from the Docker hub, which may be insecure. But what about something more recent? Like what about a 0-day? Well, it's 3-day. I couldn't quite find anything this morning, which is a 0-day, but a 3-day is still pretty scary. And it's everyone's favorite, which is a CPU bug, which is a load value injection. The details of which can be found online. But fundamentally, it's along the same lines of what we had previously with Meltdown or Spectre, and the ability that they can poke the CPU in very scary, interesting ways to gain access to the secure vault within a CPU, which is what's used to secure like encryption keys and security credentials within a very highly secured environment. And basically they can read from all of that information. Now, CPU bugs are scary. They're really hard to defend against because they're at the CPU and they're just a problem throughout everything, and also really scary because I just don't understand how that's even possible from a mentality. But these are the types of things that we're having to deal with on a daily basis. And if someone could run a container which has got this LVI, load value injection vulnerability or exploit in there, then they would access to a lot more sensitive information that we're ever used to having to deal with, and things which we would consider being secure. And so that's what we need to make sure is always secure and always available. And so we want to make sure that we can have things in place to always make sure that we are as secure as we can be. There's things like having the policy agents, having security in place at the cluster level to make sure that we're not letting anyone deploy any container which is potentially untrusted. The next one is always making sure that we can actually upgrade Kubernetes, making sure that we're always running the latest version possible. Now, when we're using managed services, this can be a problem because they are somewhat further behind of what's available today. Like the latest upstream is 1.17, but EKS is currently only at 1.15, 1.16. And so we need to be prepping and making sure that as soon as that's become available, and we want to be as secure as possible, that we are taking advantage and being able to move our system and upgrade our system in a more coherent, streamlined way, which is definitely a problem if we're doing an on-premise or manual non-managed service. We need to make sure that we are taking that into account from a security point of view, and we're not just running something old. So as a similar kind of theme, and as a summary, what are the things which we should be doing? So we want to make sure that we have a good upgrade story. If we're running an old version of Kubernetes, it's going to have security weaknesses. Things aren't going to be applied by default, and that will potentially lead to security vulnerabilities being utilized within our system. We can then go above and beyond just being the latest and greatest version of Kubernetes by customizing the configuration to have our own policies in place. Using things like the open policy agent and pod security to enforce that certain features can't be used, and enforce that only things from certain places, certain trusted places, can be deployed. We can then do things like kubebench to make sure that misconfigurations haven't been accidentally applied, to ensure that we are on a good foundation. We can go a step further to make sure that we block egress, so that if an exploit does happen, they can't steal the data or they can't connect to a remote service, to try and mitigate how much impact they could potentially have. But also just being careful with roles, like who is cluster admin? How is our cluster admin tokens being used? And does everyone actually need cluster admin, or should we start looking at more fine-grained different roles within our system? And so these are the kind of things which we need to start thinking about from the day zero. If this is all great and you want to know more, this is the talk I mentioned, which it talks about the validating webhook, and it goes above and beyond that to running exploits in Kubernetes by having Kubernetes running inside of Kubernetes. And those are really interesting attacks which I hadn't even configured. So it's a great talk. It's on YouTube. Search for it in Coldwater. And look at the Twitch stream, and you'll be able to find the video. It's on YouTube under the RSA conference. If you want to stay up to date, Code is available, and it's available for free. So that's a great way. Obviously, there's also the O'Reilly platform too. And there's also me. If you have any questions or want any more information, then do please let me know. And I will happily share some advice or point you to the resources which are available. But with that, thank you very much. It's been a pleasure doing it remote. I will check, see if anyone's been asking me any questions, because I can't do a show of hands. Is Code available for free? Yep, it's all for free. It's all available to everyone. There's no restrictions. Sometimes they will ask you for an email address, but we don't ever send you an email, or we don't do anything with that. It's just to limit some access for them. So yeah, it's available for free, and you can try it as of today, and learn Kubernetes and Docker security and all of the things which I talked about. So that's a great starting point. But yeah, also feel free to reach out to me on Twitter.